same function we just did. We took this derivative easily by regarding y as constants, very straightforward. And then we did it by limits. So we're pretty sure this is the right derivative. Okay, well, we can do higher order derivatives. We can do the y derivative of the x derivative. Okay, that's easy. We take the x derivative, and here's where I probably want to go to the partial with respect to x form, rather than putting all this in parentheses with a y subscript. It's better form to write partial with respect to y of fx, which is a partial with respect to y of 2x minus y plus 3y cubed. Okay? And then it's easy to do this. You just treat x as a constant, so the derivative of 2x is 0. Derivative of y is 1. Derivative of 3y squared is 9y. It's really simple. Once you get the habit of viewing x as a constant when you're doing the y derivative, and y as a constant when you're doing the x derivative, and as I say, you get used to that very quickly. So let's try this one. What about fyx? You know, that's a partial respect to x of fy, isn't it? And fy, just go back to this, let x be constant, fy is negative x plus 9xy squared. Derivative of y cubed is 3y squared. Multiply that by 3x. This is what you get. And I forgot to write my partial with respect to x. And the partial of this with respect to x, well, partial of x with respect to x is 1, so you're going to get a negative 1 here. Partial of this with respect to x, derivative of x is again 1, you're going to end up with 9y. It's 9y squared up here. Okay? So I just discovered my error here. Wrote a y and then write a y squared, but obviously derivative of y cubed is 3y squared. 3 times that is 9y squared. Well, you notice that these are the same. Well, okay. And you could try to think of that one through geometrically. We're out of time, so lucky for me I don't have to explain the geometry of that. Although I could explain it to my satisfaction, I haven't really worked out how I might want to explain it to your satisfaction. You could probably do it, but I'm not going to risk your time. You don't need that right now. If you have to understand the geometry of everything and how it's connected to the partial derivatives, the tangent plane, and the tangent line, or and a tangent line, then you pretty much have what you need. Okay, now when I say this is always, read it in your book, f has to be differentiable in the vicinity of x, y, or at x, y, at a point. Okay? And I guess I better look that up. And there's actually more to it. Read it in your book. There's a name for this thing. I never remember the names of these theorems. What's Fubini's theorem? What's Clairaut's theorem? Okay. And I think just because that terminology is never used when I took the course. It's kind of important to know the names. At least it's respectful to the people that proved these theorems originally, or at least publicized them. Okay, well, there it is.